Okay, so number one just pretty much asks which one has this as a solution. You can solve each and every one of these by the quadratic formula 4 times, but that's a lot. So one thing you can use to quicken things up is the fact that this is an imaginary solution, which means the discriminant must be less than 0. That will at least cut down on what you have to do. So if I do the b squared minus 4ac, I'll get 4 plus 8 as a discriminant of 12. So that's not it, because that's a positive discriminant, so that will have 2 real numbers as opposed to an imaginary. If I do b squared minus 4ac here, I'll get 4 minus 8, which is a discriminant of negative 4, so that's still in. This one, b squared is 4 minus 4ac, is 4 plus 8 again, which is 12, so again, positive discriminant means 2 real solutions as opposed to imaginary. And then b squared minus 4ac here will give me 4 minus 8, negative 4. So both of these have the same discriminant, that's negative, so they're both still options. So now I only need to do the quadratic formula twice. So negative b plus or minus the square root of the discriminant, which I don't need to recalculate, I already found was negative 4, all over 2a, which is 2. And that'll be negative 2 plus or minus the square root of negative 4 is 2i. And then once I've simplified the radical, now if it's divisible by 2, and both terms are, I can do that. Negative 1 plus or minus I. This is 1 minus I, not negative 1, so that's not right. So just to confirm, negative b is 2, 2a is 2, so it's very similar. And again, both divisible by 2, so 1 plus or minus I. So 1 plus I is a solution, but so is 1 minus I, so that is option 4. On the next one, number 2, is just straightforward long division. This one doesn't skip any terms, but if it did, I would need to fill a 0x. And I'm dividing out 2x plus 3, so 2x times 3x squared will give me 6x cubed. Multiply this by that, line it up. And then here's the big part, subtraction and subtraction. So that should cancel, and 17 minus 9 is 8x squared. Bring down my plus 10x, repeat. 2x times 4x will give me that. Okay, multiply 4x by this. Again, subtraction and subtraction. 10 minus 12 is negative 2x plus 2. 2x times negative 1. Multiply that by that. Negative 2x minus 3. Subtraction and subtraction. So 2 minus negative 3 is 5. That's your remainder. So plus 5 over 2x plus 3. And that is option 1. So long division, biggest thing, remember to subtract and be careful of double signs. Solving a basic quadratic formula. So you have to get it equal to 0 first. I don't like negative terms, so I would add that over. So it would be positive 1/2 x squared minus 6x plus 20. Some of you in our game today multiplied everything by 2, which is fine to get rid of the 1/2. But you don't have to. So the opposite of b is 6, plus or minus the square root of b squared is 36. Minus 4, a is 1/2, c is 20, all over 2 times a of 1/2 is just 1. So that gives me 6 plus or minus the square root of. Now this is 2 times 20, so 36 minus 40 is negative 4 over 1. And this, unfortunately, and kind of surprisingly to me, is where I lost people. The square root of negative 4 is the negative makes an I come out in front, and the square root of 4, we all know, is 2. And there's your answer, 6 plus or minus 2i, which is option 3. In the next one, the focus is on, do you know your cycle of i's? So I is just I, and you can have i's in your final answer. I squared is negative 1, I cubed is negative I, and I to the 4th is just 1. So it's all about how many times does 4 go in, and most importantly, what's the remainder? So 4 goes into 7 one time with a remainder of 3. So that's the same as 8i cubed. I to the 16th is a multiple of 4. There's a remainder of 0. So I to the 4th is just 1. And any multiple of I to the 4th is just 1. So that's just b times 1 minus c times an I to the 21st. 4 goes into 21 5 times. Most importantly, there's 1 left over. So that's the same as I to the 1st. So the only real thing you have to fix is that, because you can't have exponents on your I to finish. So that is just negative I. So a lot of people did this. It's a times I cubed. So it's a times negative I, not a minus I, plus b minus ci. And then you have negative ai plus b minus ci. On an open response, that was fine. If you look at your solutions, they're not quite working that way. They have kind of got your I terms together and they pulled out coefficients. So if you were to combine these, you would have negative a minus c I terms. And negative a minus c is this one, because you distribute your negative a minus ci. That's what that is. That was a little tricky to find the right answer once you even do that out. Product, so we just need a minus 2bi and 2a plus 5bi. We just need a FOIL. So a times 2a, 2a squared. A times 5bi, 5abi, minus 4abi, and then minus 10 b squared, I squared. That's an issue. That's a negative 1, so it's going to turn negative 10, negative 1 into positive 10. These are combinable. So 2a squared plus abi plus 10b squared. And they're asking for the real component. So the real component is anything that doesn't have an I, and then this is the imaginary component. So 2a squared plus 10b squared is the real component because there's no i's involved. This one was tricky for some people. Some people got it right, no problem, and then it was tricky, I noticed. The first thing you would do with any quadratic, if you're trying to figure out what the graph looks like, is you would factor. And this factors into x times x will make x squared, and c times c will make c squared. I just need to decide if it's plus c or minus c. And because the middle is a negative 2c, a double negative will do the trick. Because negative times negative is positive c squared, but minus xc minus another xc will make minus 2xc. So that really ends up being negative a, x plus b, and then x minus c twice, in other words, x minus c squared. So a, b, and c have to be positive numbers. So if we had x plus 5, our root would be at negative 5. So given that it's x plus b, our root is at negative b. So that's good, these are not, just strictly based on that. Again, c is a positive number, so if it was x minus 5, our c would be at positive 5. So our c, which is a double root because of that, and both of these bounce off of that, so that's good. So we take care of a single root at negative b and a double root at c. And then a is not a root. A lot of people had a as a root. A is the leading coefficient. It doesn't say x minus a. It just has a leading coefficient of like negative 5 or negative 4 or negative 3. A itself is a positive number, so negative, the positive number, would mean a negative leading coefficient. This is odd behavior. Degree of 2, degree of 1 makes a total degree of 3. And if it's a negative odd, it starts high and low. So tougher because we don't have concrete numbers, but still conceptually, hopefully that you can follow that. Now, again, in this next one, a, b, and c are positive. So we have a root at negative a. We have a double root at b. And we have a single root at c. And these are both, B and C are both positive numbers. They tell us that B is less than C, so putting them in that order works. And since the leading coefficient is 1, this is a degree of 1, this is a degree of 2, this is a degree of 1. So 1, 2, 3, 4. Degree of 4 overall. So it either opens up, opens down. Because that's positive, it opens up. So a single root at negative A, a double root at B, and then a single root at C will make it open up. What they want to know is, when is the function less than or equal to 0? In other words, when is the function underneath the x-axis? That's between negative A and B, and then again between B and C. So really the whole time, because it doesn't actually say just less than 0, it can actually equal 0, and right here at B it does still equal 0. So everywhere from negative A to C, it's below the x-axis, option 4. An identity is just when the left side equals the right side. So you should know just by looking at this that this one's not right, because you'd have to make this one x squared plus 8x plus 16. This one, if I distribute, I get 10x plus 5. That says 10x plus 6. This one is a little tricky. You might want to simplify this side out to C. So you'd get x squared minus 3x plus a 3x minus a 9. Those will cancel, x squared minus 9, so that works. Again, x minus 4 would be x minus 4 times x minus 4, not x plus 2 times x minus 2. So 3 is the one. This is just division. So if I wanted to do this out, I could do x minus 10 over x plus 2 to see what it equals. So x goes into x once. Multiply this times this. Line up your x plus 2. Do your subtraction. Negative 10 minus 2, negative 12. So it would be minus a 12 over the x plus 2. Looking for a factor. So if you can factor it by hand by grouping, great. But you can't. I can already see I'd take out an x squared. I'd be left with x minus 10. I can't take out anything, so I'm certainly not also left with an x minus 10. So grouping is not possible. So you can use your calculator to cheat and find a root and turn your root into a factor, or you can plug in negative 10, see if it gives you a 0. Plug in 2, see if it gives you a 0. That would be using the remainder theorem. I think I'd probably rather just graph this one. So we definitely have a root at negative 2, which means a factor would be x plus 2, not an option. We have a root at, it doesn't quite look like it's at 5. It's about 5, so that would be a factor of x minus 5, which isn't an option. And we have a root at 7-ish, so x minus 7 would work. If you want to confirm that, you could plug in 7 on your calculator and see for sure that that gives you 0. That's kind of using the remainder theorem. This one, what is the remainder when your trinomial is divided by that? A lot of people actually did long division, which is fine. You'll get the remainder there eventually. But the remainder theorem says you can just plug in 2. So 2 squared plus 8 times 2 minus 7. 4 plus 16 minus 7. 20 minus 7 is 13. Even functions. Not an even degree polynomial, but an even function. So something that is symmetrical to the y-axis. This one. That one's not even a function, so forget about it. And that one's symmetrical here, which is not the y-axis. This one, a lot of people, I think, probably have to look at everyone's work. It's a messy one, but the biggest thing is you're subtracting a product. So you're doing multiplication first here, multiplication first here. In PEMDAS, multiplication comes first. Then we'll worry about subtraction. The problem is when you subtract this this will end up being a polynomial. If you subtract a polynomial, you have to distribute. So 20 minus 15i plus 8yi minus 6yi squared. That's your first polynomial. Minus, and I'm going to treat this section just itself, and I keep the minus out in front. 5 times 4 is 20. 5 times negative 3i is negative 15i. Negative 2yi times 4 is negative 8yi. And then positive 6yi squared. So, now when we distribute the negative, 20 minus 20, gone. Negative 15i minus a negative 15i, gone. 8yi minus the negative is 8yi plus 8yi, which is 16yi. And then negative 6yi squared minus a 6yi squared is a negative 12yi squared. Can't leave I to a power in your final answer. You have to use those I cycles that we talked about. So I squared is negative 1. Negative 12 times, no, negative 12y times negative 1 is going to change that to a positive 12y. Use an appropriate procedure to show that x minus 4 is a factor. Doing long division and showing that you have a remainder of 0 is an appropriate procedure. Quickest appropriate procedure would be the remainder theorem. So if we want to see if this is a factor, plug in 4. If we get 0, yes. If we don't get 0, no. So 2 times 4 to the third minus 5 times 4 squared minus 11 times 4 minus 4. 0. So yes, because the remainder is 0. Would be my explanation. This next one gives us a function. Noticeably missing is b. But they give us a point on the function that's supposed to work. So right off the bat, I can plug in an x of 2 and a y of 35, and I can find b. So I'm going to do that first. So 35 equals 6 times 2 cubed plus b times 2 squared minus 52 times 2 plus 15. This is 8 times 6. This is a 48, so I'm going to subtract 48 over. This is a negative 104, so I'm going to add 104 over. Plus 15, I'm going to subtract 15 over. So on the left, 35 minus 48 plus 104 minus 15 gives me 76. And that's just 4b. Divide both sides by 4, and b equals 19. So my function is now this. And then they want to find all the zeros. Well, if negative 5 is a 0, then I can start by, and it says algebraically, so I can't just plug it into my calculator. But negative 5 is a 0, so I can factor out x plus 5 from that. So x goes into 6x cubed, 6x squared times. I'm going to multiply that out. Do subtraction. 19 minus 30 is negative 11. And repeat, x times negative 11x. Multiply that out. Careful of double signs here. Negative 11 minus negative 11 is gone. Negative 52 minus a negative 55 is negative 52 plus 55, which is a 3x. Bring down your 15. And then x times 3 will give you 3x. And then 3x plus 15 actually lines up perfectly, gives you a remainder of 0, as it should have. We knew we were supposed to get a remainder of 0. So the algebraically solving the rest of it is going to come either by factoring that if we can, or doing the quadratic formula. I actually think it's factorable, because two numbers that multiply to get 18 that add to get negative 11 are negative 9 and negative 2. So I can split the middle term with those, or I'm going to try to guess and check. 2x and 3x, it might be 6x and 1x, so this could take me a couple tries. But I'm going to start with 2x times 3x to give me 6x squared. And then to give me 3, it's either 1 and 3 or 3 and 1. So if I do 1 and 3, I'm going to get 2x and 9x, which is great, because that makes 11, as long as they're both negative. And I need it to be a positive 3, so it's got to be the same sign. Minus 2x minus 9x makes negative 11x. So here are my three factors, 1, 2, 3. So the zeros are negative 5, 3/2, and 1/3. That's a lengthy one. That was like a 4 or 6 point question on the Regents one year. All right, and writing functions, writing polynomial functions. This is definitely a key skill. The structure is y equals a, and then x minus your roots. So, cubic polynomial has zeros at negative 4, which produces x plus 4. Now, that 0 at negative 4 is a bounce. So that means a double root. That means multiplicity of 2. If the root's at 6, the factor is x minus 6. If I look at it, it's a single, so just to the first power. And those are my only roots. So I actually don't need that. The key is, what's a? And that's where this point comes in. Because my equation is, I haven't done the majority of the work yet, but it looks mostly written. I just need to find out what a is, and then I'll go back and change that. You find a by plugging in a point to see how far up or down this whole thing gets stretched or compressed in order to hit 236. So 36, and x is 2. Six squared is 36. 2 minus 6 is negative 4. So I can do this on the calculator, but just because I don't have one with me, I would divide over my 36 first, because I know that would make 1 equals a times negative 4. Divide by negative 4, and a equals negative 1/4. So, your equation, go back up here, switch this to negative 1/4, and be done with it. That should make sense, because it was an odd degree polynomial, cubic, and started high, ended low. So that's a good sign that you've got a negative leading coefficient. Checking the identity, simplify left, nothing to do there. Simplify right, so distribute. X cubed minus x squared y plus xy squared. Multiply plus x squared y minus xy squared plus y cubed. Combine like terms. Minus x squared y plus x squared y cancels. Plus xy squared minus xy squared cancels. Plus y cubed. So that side was never changed, and that side reduced, and they're equal. So is it? You have to answer, because they phrased it that way. Is it an identity? Yes. Okay, 18, just like 16, we're writing, okay? We don't have a picture this time, we just have details. So write the equation of a polynomial in factor form that has a y-intercept at 8, 10. Now, y-intercepts have an x coordinate of 0. So just like we plug in the 236, we're probably going to have to plug in 0, 8, 10, because that's not a root, that's the y-intercept. There's a root at 5, a double root at negative 3, and a root at 3i. So imaginary roots rather, come in pairs of conjugates. So if you have a root at 3i, that's x minus 3i. But that also means that you have a root at negative 3i, so x plus 3i. Your a is out in front, equals y. Now, I've always advised you, before you plug in your point, get rid of your imaginaries. At least FOIL this out. So that's going to be x squared plus 3ix on the outside minus 3ix on the inside. That's the beauty of conjugates. Your outer and inner are gone. Negative 3i times positive 3i is negative 9i squared. I said to get rid of the i's, so I squared becomes negative 1. Negative 9 times negative 1 is positive 9. Now we have to go find our a. So from here on out, I'm done with those imaginaries. I got rid of them. Plug in 0, 8, 10. 0 minus 5 is negative 5. 0 plus 3 is 3, but squared is 9. And 0 plus 9 is 9. I see 81 there, so I'm going to get rid of that first because I know that in my head. So I get 10 equals a times negative 5. Divide by negative 5, and a equals negative 2. I go back up to this step, right here, replace my a with negative 2. There's my answer. Sketch a graph. So it's 2, 3, 4, 5, a degree of 5, and it's negative, so it starts high, ends low. We have a single root at 5, a double root at negative 3, and we're not going to see these anywhere. So we start high, and we double at negative 3, that means we have to bounce, and then we end low. There's probably a random fluctuation somewhere else on the graph, but not enough to hit the x-axis. That's where your imaginary roots show their face. Number 19 says to solve for when f of x equals g of x. So that's going to be, when does this equal this? So 2x cubed minus 8x squared plus 11x plus 2. When will that equal negative 2x plus 3? So I add my 2x over. 8x squared. 11x plus the 2x is going to make plus 13x. And then subtract my 3 over, which will make minus 1. Now, solving this, it doesn't say algebraically, so you can really just type this into your calculator, this, and see what your roots are. And those roots are your solutions. The problem is going to be, what if there's imaginary solutions? Then you're going to have to come up with those, because the calculator can't give you those. But we'll see. Maybe all 3 of them will be real. Okay, so we have a root at 0, it looks like. I'm going to look at my table for a second. No, I don't have a root at 0. So second trace, I'm going to look for my root, left bound, right bound. My root's really actually at 0.0808659, which is obviously a fraction of some sort. So let me go back and 0.0808659 and turn that into a fraction. Not helpful. Let me think about this for a second. So I did get that one solution. I think I probably should have made the directions say any real solutions, because there really is only one x value that's real. And I noticed in my solutions down below I have that. So I think I just needed to elaborate on the directions more. I apologize. The other thing you could do is you don't even need to set them equal to each other and get it equal to 0. If you do, you're looking for the roots. But I also could type the 2 functions in separately and just see where they cross. So here's my first cubic function, and then here comes my linear function, negative 2x plus 3, and then second trace intersect will just give you the same x answer of 0.0808659. So I should have said solve for all real solutions. Number 20, because if that's not a rational number, if that's not a fractional number that I can divide out by long division, there's no way to find my two imaginary solutions. So anyway, here we are in 20. This is a remainder theorem problem. So you're given the function and you're asked what is the remainder if this function is to be divided by x plus 1. So if we had the equation, we would just plug in -1 and see. But we don't have an equation to plug into. We have a graph to look at. So if we were to plug in -1, we would have gotten -7. So that's your answer. That's what the remainder would have been. Okay? And in 21, there's only one, though, so this is a type. There's only one real root of this. It says use your calculator to find it. So you type this in. Find your one real root. 1, 2, 3, 4, 5. Okay? And then it says using that to get you started, find all the solutions. So if I want to find the other two imaginary solutions, I have to divide out x minus 5. So I'm going to do that quickly. Okay, so that went in evenly, 11x minus 55. So there's my factors so far. And now I can't factor that the rest of the way. To tee it up, I just have to do this quadratic formula. So my solutions are x equals 5, and my other solutions are coming from there. The opposite of b, plus or minus the square root of b squared, minus 4ac, all over 2a, gives you 4 plus or minus the square root of -28, and this really got people on the Connect 4 game today. The square root of -28, the negative is definitely going to be an I. So if you want to bring that I right out and make that a positive 28, do that first. Then root 28 is root 4 root 7, which is the whole number 2 root 7. So 4 plus or minus 2I root 7 over 2. Now both of these are divisible by 2, so that makes 2 plus or minus I root 7 as my other two solutions. So hopefully that helps you watch, rewatch problems that you think you need work on, and listen over and over again, slowly pausing as often as you need for explanation so that you can process it and prep for tomorrow.